Hello YouTube! Some of what we're doing today is going to be a little bit clunky without, oh, the cat doesn't like that I'm talking now. Going to be a little bit clunky without use of a second monitor, but I'll just be swapping back and forth between paper and screen for when I need something that I can write on, because without two monitors it's harder to write on the screen. So today we're going to be talking about center mass. If you've already seen the AP1 center mass one, I'd say skip ahead until you start seeing calculus. If I have the presence of mind for it, I'll put a timestamp, but who knows. Alright, so ideally, end of this, you should be able to model center of mass and use center of mass to say where something's going to be. Big parts for that are just calculating the center of mass. That's both going to be with and without calculus. And then also using center of mass velocity to predict what something's going to do in a collision. So also being able to find center of mass velocity. And my district used to make me do language goals. I'm probably still supposed to do them. Center of mass. It's the middle of the mass. It's mostly just this weird math concept. Pretty much it's the mass weighted average location of all matter in the object. So effectively, that boils down to where the mass works as though it is. It will function as a balance point. So a lot of times if you're thinking about like where you would put your finger on the object to keep it balanced, that would be what the center of mass tends to work like. Generally speaking, a good way to think of it is that it's a thing that's closer to more mass. So the more mass you have in a spot, the closer the center of mass will be to that spot. Which means that if you've got two even chunks of mass, center mass will be directly in between them. If you have 4/5 of the mass at the right side of it and 1/5 of the mass at the left, which would be a ratio of 1 to 4 of the masses, so like, I guess with the camera view, it'd be 4m here and 1m here, then the center of mass will be 4/5 of the way to the right. So it would be divvying it up so that you've got one part here and 4 parts here. Or if you have the entire length, it'd be located 1/5 of L away from the big one. So to calculate that, we're going to swap on over to paper. The equation is when you've got point masses, that your x location for your center of mass, and you can do this in x, y, and z separately from each other and then use them to get your location vector, is going to be the summation of the x location of your first point center of mass, your first point mass times the first point mass divided by the total of all of your point masses. And sort of another way that this tends to get written is x1 m1 plus x2 m2 plus, and then you do that for all of them, and you divide that by your total mass, which is frequently just capital M. So as a couple examples of what this winds up looking like, if you've got two masses of mass m and mass m, and they're located a distance of L away from each other. Then if you want to find the center mass, it'll be the x location for the first one times the mass of the first one plus the x location for the second one times the mass of the second one divided by the total mass. And when you're doing that, in particular, one of the things that's going to be pretty helpful is that you can set where you want your 0 to be. So personally, I tend to choose the furthest left mass so I don't have to deal with any negatives. But we can put it anywhere. And when we get to a slightly more in-depth example, I'll show you sort of that you can put it anywhere and get the same answer. So to start with, we're going to put it here. Now that means that if this is x equals 0, then x1 will be 0, and x2 will be L. So x1 will be 0 times our mass of m plus L times our mass of m divided by our combined mass of 2m, which gives us out Lm over 2m. So halfway along is our center of mass because they're the same mass as each other. If we up the difficulty a little bit by making it something with a mass of 3m, and a mass of m with a length of L. Then we can again put our x equals 0 on the far left, and our x2 will now be at L. Doing out the same equation, we'll get x1 m1 plus x2 m2 divided by m, total mass, and this time we'll get 0 times 3 plus L times just 1m, and we're dividing that by a total mass of 4m. That'll give us out L over 4 as our location, and we are 1/4 of the way along, so one of the fourths is here, 3 of the fourths are here, and so our distance ratio is flipped from our mass ratio. Trying it out a different way, if we had put our L at the halfway point, then this x would have been negative L over 2, and this x would have been positive L over 2. If I plug that in up here, what I'll wind up getting is negative L over 2 times 3m plus L over 2 times m divided by 4m. And that'll give us out negative 3/2 plus 1/2, which gives us 1. So, or negative 1, so negative L over 4, saying it is 1/4 of the way to the left of our start point, which is at the same location. So it really doesn't matter where you pick as your 0. Again, I just like picking the one that's all the way to the left, because, sorry, your left, all the way to the left, because that'll give you the not having to deal with negatives, which is great. Okay, another way that we can do it is to do more than one at once. More than 2 at once. If we're doing that, one of the things that's helpful to do is to, instead of thinking about it as 3 masses, we can take the center of mass of 2 of those masses. And because the center of mass functions as though all of the mass is located at that point for a bunch of things, this included, what we can do is find that center of mass location for the 2 objects, pretend there's only 2 more objects, and do it again. Now you could also do it all at once, and we're going to start out that way, but you can take more complex objects, pretend they're a single mass, and then use that location for that single mass to branch out into other masses. So doing that, if we've got a mass of m, a mass of 2m, and a mass of 3m, separated by a length of L, if you do it out all in one, with this as our location being 0, the first mass, skipping this sort of writing out everything at once because it takes a while, the first mass will be 0 and a mass of m. The second mass will be at a location of L times a mass of 2m. And our third mass will be a location of 2L, 1, 2, with a mass of 3m. And this is all being divided by our total mass of 6m. Adding that all together, we'll get 2Lm plus 6Lm, which is 8Lm, so we'll get 8/6 Lm over m. So 4/3 of the way along, which puts us at 1 1/3, slightly to the right of the 2 mass, because it is more mass on the right. And so the center mass will be closer to that. We could also do this one by taking these 2 masses and finding their center of mass first. If we do that, we'll get m plus 2ml divided by 3m. The center of mass for those 2 masses gives us an effective mass of 3m at a location of 2/3 the length away, which geometry-wise puts us here. Well, then you've got 2 masses of 3m. Their center of mass will be the midway point between 2/3 of the way along the first one and all the way along the second one, which leaves 4/3 remaining between, cut that in half, and we get another 2/3 on top of our 2/3, which puts it at the same spot that our other way did because it was 4/3 of the way along the total length of 2L. 2/3 of the way along the total length of 2L, 4/3 times L. So that's another way we can do it, is we can take our more complicated shape of 2 objects, reduce it to 1 object, and then do that with the other 2 objects. It's a little overkill when you have just point masses in a line like this, but when you have 3 point masses that are located in 2-dimensional space, or if you've got some weird 3D shapes, like a bunch of the book problems are like boxes without tops, works really great for that, because you can reduce each side of the box to a point, and then you can reduce a bunch of the points from the boxes to a point in the center of those points, and then you can go from there. One of the quick tricks for a lot of these is symmetry. So for example, if you've got a rectangle, the center of mass for that rectangle, if it's all evenly distributed, will just be a point in the middle of the rectangle with a mass of that panel of the rectangle. So you could use that to figure out where the center of mass of 2 rectangles were by reducing each of them to central points and then treating it like a 2-point mass problem. Another thing you can do that's pretty neat is if you've got center of masses for an object like this one. Well, let's say we have our radius of our circle, and we cut a circle out of that circle with a diameter equal to our radius. Now, if we do that, where this is shaded part is solid, well, if we say that center of mass location plus the amount of mass that would have been located from our cutout needs to equal our full shape if nothing had been cut out, where everything's right in the middle, with a total mass of m, if we want to find the center of mass with the whole via subtraction, via basic like algebra, we can subtract off the section that's missing from both. So what you can do is do your center of mass equation, but treat this as though this was a negative center of mass. So if we've got this shape, we can do a point mass here with a total mass of m2. You can say m1 is this thing, and the total mass of both of them is this thing. What we can do is do a center of mass calculation with a negative point of mass located here while we're doing our calculations to figure out where the center of mass will actually be, which is neat. Last thing we can do with all this, we should talk about why center mass is useful before we get into that. So, the big thing about the center of mass that makes it super useful is that external forces will accelerate the center of mass of an object or a system of objects as though that's the point they're being applied from. So if there are no external forces acting on the object, then the center of mass velocity does not change. And if there are external forces on it, you can treat it as though they're only accelerating the center of mass if you are trying to figure out how the center of mass moves. Now, if you're trying to figure out how it rotates, it's a little more complicated than that, but for now, we don't have to worry. What that also means is that collisions and explosions, the things that momentum's really useful for, which is why it's in this unit, don't change center of mass velocity because there aren't any external forces. So if there's an explosion and you know where some of the pieces are, or if they tell you about all this other stuff, there's going to be this huge paragraph of just rambling nonsense that you could spend 20 minutes figuring out what the center mass velocity would be. Or the question will tell you that before this crazy thing happens, the center of mass velocity was 4, and then ask you what the center mass velocity was at the end. And because it doesn't change, you don't need to do anything other than pick 4 because it doesn't change. So if it started out as 4, it's still going to be 4. Additionally, if you've got a heavier object, that one will change velocity or move away from the center of mass less than an object that is lighter, because the center of mass is going to be closer to the heavy one. So if the center of mass is moving at a constant velocity between two objects, those two objects, if they're different masses from each other, probably can't move with it, because the center of mass needs to get proportionally... if they're moving away from each other, they can't go at the same speed. If the center of mass is moving at... I'm doing a terrible job of explaining this, I'm just going to cut that. By which I mean, I'm sorry for wasting your time, I'm not going to edit the video. But the center of mass velocity will track in a way that's a little bit slower than you might expect if two objects are moving away from each other, or if two objects are moving towards each other. Because for every little bit that the heavy thing moves, the center of mass will have to move less, because if it moved the same amount, it would be getting either further away from the heavy thing than it should be, or closer to the heavy thing than it should be. And then the last thing is that you can use center of mass velocity to find the center of mass, and then use that, if you know where one of the objects is, to figure out where the other one has to be. So doing like a super quick example of that. If you have something like this, where you've got this object of mass m and this other one of 2m, and you know that the center of mass should have moved over by 1, 2, we'll call this 1, 2, 3, 4, 5, 6 boxes, and you know that now the lighter object is 1, 2, 3, 4 boxes away after an explosion. That's only possible if the center of mass and mass m are in the correct location compared to each other. So the mass of 2m needs to be such that it is half the distance away from the center of mass, so that our center of mass is still located closer to the one with a mass of 2m by a distance ratio that is inverted from the mass ratio. And so you can draw little pictures like that to be like, oh, this is where this one has to be, and solve some problems pretty quickly that way. If you are not interested in solving problems quickly, you can do all of this with calculus. And this is particularly useful for if you have a really weird shape, or if you have a situation where the density of the object is non-linear. So to do this, the x location of the center of mass is going to be the integral of x dm divided by our total mass. Now, this is a problem because dm and x are not the same variable, and both are variables. So you can't actually integrate this. So a lot of times what you'll have to do is figure out x in terms of dm. And to do that, most of the time what you'll be using is that the density of the object is going to be equal to either dx dm if it's a linear density, or dA dm for the area, so it would be dx dy, for a sheet mass density, which I think that's the symbol for, and dV dm if it's a full-on object density. So that's one of the things you can do, and most of the time this will be the one you'll be using, and you'll get it as a function of x. So what you can do is you can say that, I'm sorry, I flipped these. Density is mass on top. So this one should be dm dx, this one should be dm over dA, and this one should be dm over dv. So most of the time if you're solving for x, dm, all you really have to do is get dm equals whatever lambda is in terms of x times dx, and that will give you what dm is. So if you take this and plug it into your equation, and then find a way to represent your total mass, you're fine. So, doing an example of that, and we're actually going to do a couple quick examples, one of which is going to be the base problem, and then we'll just modify the base problem a little bit. So we've got a situation where we've got a rod that's getting heavier as we go to the right by a fixed amount. So our mass density is equal to some constant value times how far we are along the rod. And so we'll get this thing that's lighter on the left side and heavier on the right side, and we're trying to find the center of mass. In order to do that, we'll be saying that the x location of our center of mass is equal to the integral of x dm over m. And we need to find a way to represent dm, and we'll need to find a way to represent our total mass. To find a way to represent our dm, we can do this thing up here, where we say that our density of the whole object is also going to have to be equal to the density of a very tiny piece of mass at that location. And that will have to equal k times x. Multiplying each side by dx, multiplying each side by dx, we'll get that our tiny slice of dm is going to have a mass of kx times the tiny slice of width that's occupying our space. So we're basically cutting it up into this tiny section of dm, and we're saying that that mass there is going to be equal to the density times the width that's of our specific little chunk. Great, so now we've got a function for n. So integral of x from 0 all the way out to the length of the whole thing times kx dx divided by our total mass will give us an answer. The problem is we don't know our total mass, but we do know our mass density. So if we integrate our equation for our density with respect to our entire length, what that'll give us is the sum total of all of the mass at the location. So our total mass in this case will be equal to kx squared over 2 evaluated from 0 to L, or k L squared over 2. Coming back over here, if we do a very similar looking integral, we'll get k x squared over 2m evaluated from 0 to L. And if we plug in, oh, sorry, brain fart. This is an x times x, which is x squared. I need to integrate x squared. I should just have written this out. So we'll get kx squared divided by m, and we're evaluating that from 0 to L. So this is x to the third over 3. I thought that was going to cancel out in a way that it shouldn't have. So k over 3 over m, L to the third, will be equal to our x location of our center of mass. helps if you can see the whole thing. Giving you a second to copy that down now. Okay. So the x location for our center of mass here is going to be 3k over 3 L to the third divided by m. Well, we can take our equation for m and plug that in. And when we do that, we'll get k over 3 L to the third divided by KL squared over 2. So 2/3, the k's drop, L squared drop, times our length will be where our center of mass is. And so we have one object where the mass of that object is equal to the mass of the whole object, or KL squared over 2, where that's located effectively that we can treat our rod so that all of the mass is 2/3 of the way along the length. So when we go to do our second problem, where there is a ball with a mass of 2 capital M being the total mass of the rod, attached to the left end of the rod, then we've got a situation where we've got this big old chonker, and we've got this rod of mass M and length L. But we can treat that like it's this one dot with a mass of 2m from the ball, and 2/3 of the way along, one dot with a mass of m. And when we do that, we can just go back up to the stuff we were doing for our normal equations, where we've got this is our 0 location, so 2m times 0 plus 2/3 L times m divided by our total mass of 3m, giving us 2/3 over 3, or 2 over 9, times the length as our final location for the center of mass on our new object. The one last thing that we should really talk about is how to find center of mass velocity. So if you are looking for center of mass velocity, the good thing is that because x center of mass is equal to the sum of x, or the integral of x dm, divided by mass, if we take the time derivative of that on both sides, because mass isn't changing with time, just position is, we'll get that our velocity for a center of mass will be equal to our summation of our velocities times our mass divided by our total mass. Well, the summation of all our velocities and masses is just going to be the same thing as saying the summation of all our momentums, because mass and velocity is momentum. So this is going to be our total momentum. So if you're looking for the center of mass velocity, it's just going to be equal to your total momentum divided by your total mass. And that's a big part of why it doesn't change, or that's a way to understand that it doesn't change, because it doesn't change because our total momentum doesn't change and our total mass doesn't change. In order to get the center of velocity to change, you would have to either change the amount of total momentum you have with an external force, or change the amount of mass you have by somehow removing mass from the system. And that's pretty much it. So goodbye, YouTube.